Our screen recording for the geography students. So, velocity is a vector quantity. That means it's going to have what just happened to my screen? Let's try that again. Magnitude and direction. Okay. Now, last week, we looked at position time graphs and we said we can get heaps of information from a position time graph, where they started, how long it took, where they travelled, what their velocity was, what their distance was, all these things. You can also get a lot of info from velocity time graphs. So now, you've got to be careful. Our velocity time graphs are VT graphs. Please don't be so rude. If we place meters per second and then time in seconds, let's just do a very simple, an object travelling at 2 meters per second for 4 seconds, okay? So now this is not a position time graph. If it was a position time graph, you would see it getting larger on the y-axis by 2 every second. It would start at 0, then 2 meters, then 4 meters, then 6 meters, then 8 meters. If you calculated the gradient of that, you would find it to be +2. Well, we're going to put the gradient on its own graph. So we take that gradient, we chuck it there. But we can always go backwards. What this means is the velocity means that every second they travelled 2 meters. Every second, another 2 meters. Every second, another 2 meters, and then I didn't draw my scale constantly, so let me just bail out, spread that out a little bit. So you could just imagine every second add a block. That block has a dimension of 2 by 1. Well, that's area. So could you please write, however you write it, area equals velocity times time. Here's our velocity, there's our side length there, velocity, and here's our side length here, which is time. We have an equation for that. That's going to be displacement. Displacement. So the area under a velocity time graph can give us displacement. Let's try one now that gets a little bit trickier. Let's try an increasing velocity. So let's say velocity on the y-axis, time on the x. Let's say that we started off 0 and we accelerate. In a time of 4 seconds, we accelerate up to 10. All right, so at the start we were stationary, then we're getting faster and faster and faster. After 1 second, we're probably at about 2.5. After 2 seconds, we're probably at about 5. After 3 seconds, we're probably at about 7.5. Well, how do you think I could get the area underneath this? Not Pythagoras, area of triangle. Half base times height. So in this case, we could just say, all right, every second they're travelling further. If we looked at the blocks, each subsequent column that I'm drawing here is getting larger and larger and larger. And that is true. If you're accelerating, you travel more distance in the next second than you did the previous second. Well, let's just quickly do a half base times height. That's going to be a half of 4 times 10. That's going to be 20 meters. Okay, so the area under that, in that 4 seconds, they travel 20 meters. We could do a decreasing velocity. Let's try this one. Boom, just draw it nice and straight. V, meters per second. Somebody give me a starting velocity. 5. Somebody give me a finishing time. 10. Okay, so what could this be? This might be you roll a ball along, maybe playing lawn bowls. This could be a good example. You throw your lawn bowls, it rolls along the green, it started at 5, and then as friction of the grass slows it down, you watch it, it takes 10 seconds to come to rest. Have you guys done lawn bowls in sport PE? Yeah. You guys go over to the Claremont one? Well, let's see what the area is under this one. A half base times height, 5 times 5, 25 metres. So that's an accurate example of the distance of a lawn bowl. Remember, with position time graphs, we can make it even trickier. Let's have a varying velocity. Let's say, that's in metres per second. Let's look at a car taking off from a set of lights. They accelerate up to a cruising speed of 15. They cruise along for a constant speed. Oh, let's say it takes them, I don't know, 4 seconds to accelerate up to that speed. I don't know. Then they they cruise along for about, I don't know, another 10 seconds. And then the lights turn orange in front of them. They've got to slow down because the lights are turning red. So they slow back down to 0. And let's say it takes them another 4 seconds. You go, okay, we can handle this. You could either turn it into a trapezium or you can just turn it into a triangle and a rectangle. So let's have a go at this one. That is going to be a half of 4 times 15 plus, what's this one going to be? 15 by 10. Plus, so you could call this area 1, area 2, area 3. So this one's going to be the same, a half of 4 by 15. Have I made a mistake?
No, could you turn it to 2 rectangles?
2 rectangles?
Well, 15 by 10 and then 4 by 15.
You mean put that one over here? You could, but I want you to show you're working out. So let me just make my arrows a little bit smaller because I just want to do another line of working out just here. What's 2 by 50? 30 plus 150 plus 30. So that total journey, the displacement is what? 210 metres.
So I don't get, because can't you use Pythagoras as well?
No, so we don't want this side length. This doesn't really mean, the length of that doesn't mean anything to us. It's the area under. So I will often try and shade. Can I get a highlighter that's in grey? I want the area underneath the curve. Okay? The area underneath that black line will tell me the displacement in the directions. Obviously this could be, north. On your axis you might have velocity meters per second north. So all of a sudden we know our car is accelerating north, then cruising at a constant speed north, and then slowing down and coming to rest. Okay? All right. Let's just do question 2. We had, let's just make this top one north. All right, I'm writing a lot of stuff. So this was a north, and so then we can go, all right, we now know that the displacement was north as well. Okay? I've just added some more information to our axis. So that could be somebody that's accelerating in a northwards direction. In 4 seconds, they displaced themselves 20 meters north. Because now, let's go this way. A steady increase in speed in the opposite direction. Well, if that's north, then south is down here. And now I'm going to draw that. Somebody give me a final speed. Whoa. Okay. And somebody give me a time. 5. Well, that's pretty fast. Okay. That's like MotoGP speed. Okay. The bikes are starting on the starting grid. They're facing south. Ready, set, go. They accelerate up to 200 kilometers per hour in 5 seconds, which is not actually. Let's just add a 15. There we go. That makes it a little bit more realistic. This could be a drag race down at the Kwinana Motorplex quarter mile. Well, every second, they're covering some area. Every subsequent second, more area, more area, more area, more area, more area, more area. The total area, half base times height. Well, a half of 15 times, let's put the negative in now. Now what's that? That's 30 times 15, 300, negative 450.
Why is it negative?
Good question. Why is it negative? I think I did one of these things. I think I made a convention that north was positive and south negative. So now our area, this area is below the x-axis. So anything above the x-axis might be, north, positive. Anything below might be south, negative. Okay? So we can then obviously say 450 meters south, because it said in the opposite direction to question number 2.
And would that be almost 45 degrees south?
No, well, okay. Don't try and. This is not a bearing. This is just. This number. Imagine that every second we looked at the speedo of the bike or the car, and so after 1 second it read 4, then 8. Wait, hang on. 60 divided by 15. Yeah. 4, then 8, then 12, then 16, 20. Every second it's increasing. So imagine you're watching the speedo going from 0 around to 60.
It's how fast it's going.
So it's over time, your velocity is increasing. All right? So over time, you're creating an area underneath your x-axis. Okay? Over the page, worked example. We'll do that worked example in a moment because my graph has suddenly cooked itself. Let's go over to these two. Could you please, simple sketches, all right? You don't need to get your ruler out. It doesn't need to be scaled, but you've got to put the important information on the y-axis and x-axis. So we've got all the information. Let's go V, meters per second, time in seconds, 0, 20, 4. Boom. All right, that's all we need. So 2 by 20, 40 meters. All right, that's as much as I want you to do. Now for the next one, I'm going to try and draw this little motorcycle. Marc Marquez, there we go, close enough. Marc Marquez is approaching a corner. He's somehow off the road. Let's try that again. Approaching a corner. Okay. He needs to decelerate. He approaches turn 1 at 95 meters per second. And he then needs to decelerate to 25 in a time of 5. So he's starting there. So he's not coming to rest, he's coming to the speed that he can safely turn the corner. If he's travelling any faster than that, then he might fall off the bike or run wide and not be able to complete it. So now, here is his velocity time graph. Look what we've made. We've got a trapezium of some sort. Yeah? Is it called a trapezium? It's a trapezium. Is that the shape? A trapezium. Where one side length is higher. I don't know. Let's just split it into.
It's like a half.
It's a half. I don't know. I never paid attention in maths. Your total displacement, S, equals. Well, let's find the area of number 1. That's going to be a half base
70.
Times 7. Very good. 70. Then we're going to add the length times width. So that triangle is, or let me just cheat, I've got it here, 125 and 175. Okay. So that should hopefully make sense. You're heading towards this turn number 1 at 300 kilometers per hour. You hit the brakes. In 5 seconds, you're now down to 25 kilometers per hour, and you can then tip in and get around that corner. In that 5 seconds, you've traveled 300 meters forward. That is why, I don't know if you've ever seen car racing, supercars, MotoGP, NASCAR, they will often have little turn markers that say 300, 200, 100. Huh?
Yeah, it's not 25 times 5 is not 75.
Yes, 125.
125, yeah, thank you. My number is still correct. Thank you very much. So these little turning markers, they are for the racers to know how far it is to the apex, which is where you turn the corner. And so the aim of the game is to try and brake as late as possible. So most motorcycle riders or racing car drivers will know at every corner they can start braking at a certain point. And it might be, in this case, it might be the 300 meter marker. Maybe on the next lap, he tries and brakes at the 250. But if he leaves it too late, then he won't be able to get down to 25 meters per second, and by the time he hits the apex, he's traveling too fast. And you see this all the time in races where they run wide. And if you run wide, that's bad, because then you end up getting overtaken by the person that broke at the right point. Okay? All right. Last example, then you will do the next, and then we will look at Logger Pro in the last, say, 10, 15 minutes. Here's the cool thing. Everything in physics is cool, but we can use north, meters per second north, as positive, in which case south would be negative. So this might be a warm-up drill for PE. Your PE teacher says, all right, guys, I want you to run out to the cricket nets, and as soon as you touch the cricket net, I want you to turn around and start jogging backwards to me. Okay? So, you take off at 2, 4, 6, negative 2, negative 4, negative 6. You take off at a constant speed for 10 seconds. Then, you turn around and you start jogging backwards for 8 seconds. Now, obviously, if you're running out at a faster rate for a longer time, they're not going to be back yet, are they? They're still jogging back. At 18 seconds, they're not back to the PE teacher. Well, look what we've done here. We've just got your displacement north, and this is going to be your displacement south. On the top, you've got a positive area, and at the bottom, you've got a negative area. Yeah? So now you've got to be careful. We could do distance, it's just the total area. Or we could do displacement, where the area above is positive and below is negative. So now let's give it a go. We could say that the total displacement is going to be, let's go, plus 6 times 10 minus 4 by 8. So that means you jogged out 60 meters north. That's the area under the first triangle. And then you jogged backwards. Sorry, you ran out 60 meters north. Then you jogged backwards 32. Yeah? Does this all make sense? I see a couple of people nodding. You go, okay. The teacher looks at his stopwatch. It says 18 seconds. He looks up. He goes, where are they? What displacement are they after 18 seconds? Well, let's just combine them. We'll go that, take that. Calculator says plus 28. We'll say that they're still 28 meters north from the teacher. Okay? This is almost going right back to our first lesson when we said You're just going to assign one direction as positive, the other direction as negative. What was the total distance that the student travelled in the 18 seconds? What is it?
10 meters.
It's not 18 meters.
92? Who said 92? Kid at the back. Have a look. With distance, we just ignore the plus signs. Don't worry about north and south. I ran 60 metres, then I ran 32 metres. I have run 92 metres. We could go back now to look at what was the average speed, what was the average velocity, distance over time, displacement over time. You're going to get two different answers. You could do 92 over 18, that would be your average speed because you travelled 92 metres. But your average velocity is going to be that divided by 18. 28 metres north divided by 18. So you can get all of this information. Now, you try. Now you try it for me, please. Sketch. Doesn't have to be scaled, but all of the important information needs to be on your axes. So, velocity, meters per second north. Time in seconds. 5, 10, 15, 20. Negative 5, negative 10, negative 15, negative 20. You're going to go for 100 seconds, then you're going to stop, then you're going to go for 80 seconds. Okay, yes? Guitar lesson, but you're going to miss out on all this fun. That's all right, you can watch the YouTube video this afternoon. Put your headphones in and chill.
So where's the camera?
It's screen recording this screen, all right? So
Can they hear your voice?
they can.
So doesn't that mean that you answered that?
No. We're not communicating with the dead. No. All right. So that's their journey. We'll ignore the fact that it takes a little bit of time to slow down. We'll just say constant speed, then stationary, then constant speed. All right, so we're getting a positive area, we're getting no area because they're stationary for 20 seconds, then we're getting a negative area. I'd like you to do exactly the same. Find the two areas, assign one as positive, one as negative.
What is the S mean?
Displacement. Remember our little vectors? So now you can do your fancy maths. The sum of your displacement is S1 plus S2 plus 20 Now this is almost the same example as the students running. You're going to have a greater north displacement. You're going to get plus 2,000 and then minus 1,200. That's it. Yo. No. Well, then you can pee into the empty bottle. All right, hurry up. You race straight back. Don't even wash your hands. Just get straight back. All right. In summary, let's just compare. Students will often confuse position time graphs with velocity time graphs. So let's just quickly remember. We're putting time on both of the x-axes. Okay? For our position time graph, we're going to put displacement or distance. Velocity time graph, we put velocity, hence the name. Well, for our position time graphs, the gradient was velocity. The area underneath gave us nothing useful. Doesn't really help us. A horizontal line on a position time graph meant that your position wasn't moving, so you were stationary. A positive gradient would represent a positive velocity. A negative gradient would represent a negative velocity. Now, we're jumping ahead of ourselves a little bit. This summary should really be a few pages further down, because tomorrow we're going to look at what the gradient of a velocity time graph is telling us how our velocity is changing with respect to time. That's acceleration. That's going to be tomorrow or Friday, whenever I see you next. But what did we learn today? What does the area under give us? Or displacement. Displacement. Okay? If your velocity time graph is a horizontal line, what might that represent? Same speed or a constant velocity? A horizontal line means that your velocity is not changing. And then obviously a positive gradient would mean a positive acceleration. Negative would be negative acceleration. These ones we will work, it'll take a few lessons to get familiar with. We'll get to that tomorrow. But for now, who here was able to download the Logger Pro 3? Yes, I knew I could count on. He's in Noke. He's a good kid. Get your laptops out, guys. I emailed you a Logger Pro file and an instruction to download Logger Pro 3. Now, McClarty, let's have a look and see.
Not the same problem as McLeod.
Well, thank you for voicing your issue. Let's just open up the software center and see if we can find it. Because I'd like you guys... Today I'm going to do a quick little tutorial, and also maybe next week I'm going to show you how to use motion capture. We're going to film ourselves throwing objects around. Logger. There he is. Get the 14.1 and then get the update afterwards. So get the 3.1, 4.1. Got it? Don't you lie to me, child.
Mine's not there. I've got bull shots.
Search in, just type in LOGG.
I did exactly what you
Okay. Well, you must be in a different...
He's a new kid.
Is it pick, play, post?
Can we go into... Okay, remove the search. Go into filter and go science. There it is. Download that one.
Is it called Logger Pro?
Yeah, 3.1, 4.1. Download that one first. Go into science. Go into science. Wait. I think you need to ask IT to change your parameters. Apparently they don't think that you are a science student. You need to download science applications.
Mine's not there.
Alright, could you at recess or lunch? Or I might even send a request now saying some of my 10 Physics 7 kids can't.
Where do I see the...
Alright,
So where do I find the science section?
well, go into filter. Go most recent, sort by go publisher name A to Z, no, application name A to Z, and scroll, just slowly scroll down to the L, go back up to the L, alright. Okay, I will send an IT request. Many of my students only have coding in a filter. Okay, let's go.
So you thought I was lying? I've never done it.
No, I just didn't trust you. Sort of same thing, isn't it? What does it say? Their filter only brings up coding.
And it's not there. Yeah.
What are you doing?
That's the like, just like
That's just
I get those things.
Okay. Let's see if they come back with anything. All right. Who here has Logger Pro 3 downloaded? You're all lucky kids. Okay. Well. All right, and it's installed. All right. I'll work slowly then, because I'm thinking on my feet. What the heck am I going to do? Maybe you guys could just do more questions.
Oh, go play the horse race because no one's here.
Maybe. Yeah, maybe. But I'll need to get a HDMI cable, which I don't have on.
What's the horse race?
Don't worry about it.
It's the best thing.
Okay, guys.
Is it a Mr. Mariah?
You bet on horses and if you
Boys, once. Shh. Calm down. Calm down. Calm down. Calm down.
I love horses.
Boys.
Horses are exciting.
I'm still screen capturing. I probably will end up giving up on the screen capture. But once you've downloaded Logger Pro, I want you to open up the .cmb file that I emailed you this morning. It's a very small file. This shows the motion of an object from 0.4 seconds into the video to 1.4 seconds. You know what it was? It was me with an object. I threw it up and then I caught it. And then I stopped tracking. So this is the motion of the object as it was in the air. All right? So it started off at a certain height, it traveled up to a certain height, and then it came back down. Okay? Now, looking at this, I could do a number of things. I can bring this down. I could maybe click here. I could highlight the data. It will give me the delta. See down here, delta T, 1.07. That's the distance from the first dot to the last dot. That's saying how long it was in the air for. What do you think the delta Y is? How high it got. So it's saying from the lowest dot to the highest dot, 1.17. Okay? So I'm expecting, remember our instantaneous velocity? I'm just going to click on my tangent. At the start, I want you to look at the start, it's telling me that the instantaneous gradient is about plus 4.3. Just remember these numbers approximately. And then if I bring it along to the last dot, it's about negative. Look at that, negative 4.3. Interesting. It's telling me that it left my hand at 4 meters upwards and it returned back to my hand at 4 meters downwards. How surprising. And it took about 1 second to do that. Now, when you get these kinds of graphs, gentlemen, and again, we will do another tutorial when everyone's here and I'll teach you how to get these kinds of graphs from videos. Click on the y-axis. Press escape first. No, where's my... Click on the y-axis and you can look at different things. Instead of looking at the y position, let's look at the y velocity. Let's get a velocity time graph. Ooh, look at that. Ooh, yes. All gasp excitedly. Now, this is now how the velocity of the object changes over time. Have a look at the top. At the start, it was traveling at 4.3 positive, and then about halfway along, its velocity was 0. Well, that's when the object was up the top, right at its highest point, and then it turned around and it fell back down. The next half of the journey, you'll notice that its velocity is now negative. It's now travelling back. And when I caught it at the very end, it hit my hand -4. Okay? Now, the great thing, who has this document open on their laptop? 1, 2, 3. Excellent. Again, we will do more tutorials, but you can do really cool stuff. You can highlight the upwards journey. I want you to highlight that part. And there's a really cool button right there that's going to give us the area under the curve. So if I click that one, which looks like the roller coaster slide, boom, it gives me the area under as 1.16 meters. So that is the positive displacement of the ball from when it left my hand to when it got to its highest point where it was stationary. It displaced itself positive 1.1. Now, we said that this is the return journey when it came back to my hand. What do you think the area under this is?
Negative 1.1.
Negative 1.1. Well, let's just check. If I highlight from 0 down to here and do the same button, close enough. Negative 1.1, to the nearest 2 centimeters, that's pretty damn accurate. Right? So, and again, it's just taking, see what it's done? It's made a very complex shape. It's just joining the dots, dot to dot, right? And it's basically doing all of the maths for you. It's basically going area of triangle, area of trapezium, boom, 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 add, total area 1.08, negative. Alright? If you add those two together, you'll get plus 1.1 minus 1.1, total velocity is 0.
Can it find the distance traveled?
Before we answer that one, Ryan, what if I highlighted the whole thing? It might just add them together and they might cancel out. Let me just highlight the whole journey and go, what is the total displacement? 3 centimeters. 0.2. So maybe I didn't catch it in the right spot. Maybe my hand moved 3 centimeters from me throwing it to catching it. Distance. Now, what we might need to do, Ryan, is just do them separately and add them together. So that's an interesting thing. The ball travelled a total of 2.2 meters. It just happened that 1.1 was up, 1.1 was down. The ball travelled 2.2 meters. It might have had an average speed, but its average velocity was 0 because it finished where I started. Okay, let's finish it there. We'll play some Japan World Cup. I just need to go and get a HDMI cable. Okay? Please remember this. I'm talking to everyone right now. Your homework is due on Friday, and that is your homework sheet 3 and homework sheet 4. You now have all of the knowledge in your brains to complete... Oh, homework sheet 5. Oh, I didn't realise. Just do homework sheet 3 and 4. We'll eventually get around to homework sheet 5 for some fun stuff. Okay? All right. We'll stop the recording.